Good afternoon, ladies and gentlemen. Let me introduce myself. My name is Vorobyeva. A few weeks ago, I defended my PhD, and since 2019, I am a junior researcher at the Marchuk Institute of Numerical Mathematics of the Russian Academy of Sciences. The theme of my today's talk is the evaluation of external forcing and initial conditions contributions to decadal predictions of the INMCM5 climate model. Timescales from year to decade are very special for climate state predictions. In this timescale, the influence of initial conditions becomes small, and the influence of external impacts on the climate system is still not strong enough. It's required to study the mechanisms of predictability on this timescale. Nevertheless, such kind of prediction is very important. Its importance is dictated by the growing demand from the sectors of the economy that are sensitive to climate parameters, such as energy, agriculture, and healthcare. The characteristic period of long-term planning usually fits within the considered time interval. Therefore, we adhere to the following objectives in our study. First of all, the evaluation of the INMRAS climate model scaling prediction of the leading large-scale modes of long-term variability for up to 5 years ahead. The second, assessment of forcing and initial conditions contributions to predictability of the Arctic sea ice area and the upper 300-meter water layer heat content. So there is the family of coupled climate models with different configurations named INMCM and developed at the Institute of Numerical Mathematics of the Russian Academy of Sciences. This study is based on the experiments carried out with the model version INMCM5. It consists of 3 main blocks: the block of atmospheric dynamics, aerosol block with the same resolution as the atmospheric block, and the block of oceanic dynamics. Initial conditions for decadal hindcasts are generated applying the bias correction algorithm in order to avoid model climate drift. Here we used error interim and error 5 reanalysis data for atmosphere, soil, and land, and also we used SODA and GAMS-NEMO analysis for ocean and sea ice. After that, we carried out a series of 15 model experiments for each year from the range of 1980 to 2020. Each experiment began on the 1st of November and had a duration of 5 years. Now let's move on to the results of the experiment. The modelability of large-scale processes prediction might be an important source of multi-year predictability, since due to the global teleconnections, they determine the future development of the Earth's climate state. And we will start from El Niño Southern Oscillation. The quality of the El Niño Southern Oscillation reproduction by the INMCM5 climate model was assessed using the Oceanic Niño Index. So here you can see anomaly correlation coefficients of the ONI index time series for the INMCM5 climate model or decadal hindcasts for the first years of experiments and NOAA observations. The red line here shows the segment with the largest gradient. It belongs to a time interval from March to May, and that means that our climate model reproduces the spring predictability barrier of El Niño Southern Oscillation. For the second years of decadal experiments, the predictability, unfortunately, is significantly reduced for El Niño Southern Oscillation. What about Arctic sea ice area? Here are anomaly correlation coefficients of the total Arctic sea ice area based on the decadal hindcasts of the INMCM5 climate model and the Nimbus 7 satellite data. We can see that even for the second years of experiments, anomaly correlation coefficients are still high. And that means that our climate model indicates the possibility of the Arctic sea ice area prediction for the first 2 years. Also, we can see that there is a decrease in the predictability of the Arctic sea ice area in winter and spring, and its increase in summer and autumn. This is the Arctic sea ice spring predictability barrier. Many studies also have shown the evidence of the Arctic sea ice predictability barrier. The causes of spring predictability barrier are the following. First of all, there is a sharp increase in predictability at melt onset due to positive sea ice albedo feedback. That was stated by Bushuk and co-authors in 2020. The second reason is that summer months have little sea ice coverage and little intrinsic memory of sea ice, and therefore require another source of memory to provide winter sea ice extension prediction skill. that was stated by 1¼ in 2022. Now let's have a look at total sea ice area. Here is the value for our climate model decadal hindcast in blue, and in red here are the values of total sea ice area for Nimbus satellite data. We can see that our climate model reflects the overall trend of sea ice shrinkage in the Arctic from 1980 to 2020, which is also present in satellite data and attributed to global warming. And on the right figure, these are the Arctic sea ice area anomalies. We can see that our climate model also demonstrates the correct sign of the Arctic sea ice anomaly in almost all years since the end of 1980s, and in the early 1980s, the discrepancy in the sign of the anomaly with satellite data can be explained by the insufficient quality of satellite data, because during this time the net of satellites only began to spread. What about North Atlantic oscillation? Here are December, January, February NAO time series of our climate model hindcasts in red for the first years of experiments in the left figure, and for the second years of experiments in the right figure. In black, there are time series of ERA 5 NAO index, and in blue, this is the ensemble spread. We can see that for the first years of experiments, anomaly correlation coefficients reaches the value of 0.41, and for the second years of experiments, minus 0.17. That means that the model skill in the December, January, February NAO index prediction for the second years of decadal experiments is low, but prediction of the NAO in multi-year timescale is a problem of current interest for the most operational prediction systems, and that was stated by Smith and co-authors in 2016. Now let's move on to quasi-biennial oscillation. Here are anomaly correlation coefficients of the equatorial zonal wind speed at the height of 30 hectopascals based on the decadal hindcasts of the INMCM5 climate model and the CDAS reanalysis data for different lead times. We can conclude that INMCM5 climate model shows acceptable results in the QBO prediction for up to 5 years ahead. Now let's move on to estimation of forcing and initial conditions contribution. We have decadal experiments, which include information about initial conditions tied to real date, and we also have historical experiments from 1850 to 2014, where all impacts on the climate system corresponded to 1850 and didn't change over time. So these experiments do not include information about the real state of the climate system by the required date. We also have continuations of these historical experiments, the scenario experiments, which were calculated according to SSP3 and RCP7 scenario. Therefore, the difference between anomaly correlation coefficients in decadal and historical plus scenario experiments show initial conditions contribution to predictability. So let's look first of all at contributions of the to the seasonal predictability of the Arctic sea ice area. Here are the Arctic sea ice area anomalies for decadal predictions in the left figure, and for historical experiments on the right figure. We can conclude that decadal experiments reproduce the observed anomalies better, as we expected. And here are the anomaly correlation coefficients of the total Arctic sea ice area for decadal experiments above in the table, and for historical experiments and their continuations below in the table. We can see that both forcing and information about initial conditions make contribution to the Earth's climate state in spring. And during summer and autumn, only the contribution of forcing is important, since the anomaly correlation coefficient values for historical and scenario experiments exceed those values for decadal experiments. And what about the heat content anomaly? So here are anomaly correlation coefficients for heat content anomaly based on the decadal experiments of our climate model on the left figure, for historical experiments, and for the difference between decadal and historical experiments. We can see that the improvement in the quality of the upper 300-meter layer heat contact prediction is mainly in the Pacific Ocean. This is because the decadal experiment correctly shows the PDO phase. So in the beginning of the 21st century, there was the change in the Pacific decadal oscillation phase from positive to negative, and only decadal experiments capture this change. Moreover, in the Arctic, taking into account the initial state in decadal experiments leads to lower anomaly correlation coefficient values. And this is consistent, for example, with the research of Smith and co-authors in 2019. In the North Atlantic, where decadal prediction systems traditionally show good prediction skill, our climate model shows satisfactory predictability already in historical experiments, and setting the real initial state doesn't lead to a large improvement in model skill there. So now let's summarize the main points of my talk. First of all, the INMCM5 climate model skill in decadal predictions for up to 5 years was evaluated. The presence of the in-source spring predictability barrier for the first years of decadal predictions is shown. For the second and subsequent years of decadal hindcuts, the quality of the in-source prediction is low. The decrease in predictability of the Arctic sea ice area is shown for winter and spring, and this increase is shown for summer and autumn. High quality of the Arctic sea ice area prediction is maintained also for the second years of decadal experiments. The INMCM5 climate model shows acceptable results in the quasi-biennial prediction for up to 5 years ahead. The model skill in December, January, February NAO index prediction for the second years of decadal experiments is low, but prediction of the NAO in multi-year timescales is a problem of current interest for the most operational prediction systems. It was shown that the Arctic sea ice area predictability of the next summer is affected mostly by forcing, while predictability in spring is determined by both information about the initial state and forcing. The improvement of anomaly correlation coefficients of the upper 300-meter layer heat content anomaly by setting the real initial state occurs mainly in the Pacific Ocean due to the correct Pacific decadal oscillation phase. In the North Atlantic, where decadal prediction systems traditionally show good skill in prediction, our climate model already shows satisfactory predictability in historical experiments, and setting the real initial state doesn't lead to large improvement in model skill there. So thank you very much for your attention. Here is my email. You can contact me in case of any questions, or maybe you have ideas for further collaboration. So you are welcome. Thank you very much.